All right, guys. So just before we move to the next topic, let's just review what is quotient rule and what is product rule, and why not do that all together. This involves main operation is quotient rule. Do you agree? But to take the derivative here, you have a product right over here. So it's within a quotient rule, you have a product rule. The exercise is rather tedious. But here is what you do. You just square the denominator. You copy the denominator and multiply by the derivative of the numerator minus the derivative of denominator multiplied by numerator. Here I just ran out of space and I just put it in this box. Now, when I carry out the derivative, what happens? This is just squared. This is copied. This is the derivative of product rule here. You with me? So the derivative of the product rule of this part is just derivative of first function times the second plus second times derivative of first plus the derivative of 10x, which is this, minus the derivative of this function, which is 15x squared minus 7 times the numerator function. There is absolutely no need to do any more work because, guys, do the minimum you have to. Look at when I give you the exam. Read the instructions and do the minimum you have to. Don't do more, don't do less. Clear? If I say find the derivative, it doesn't mean you have to do it by definition. You can do it any way you like. Some ways are better than others. And by the way, guys, since it began, I mean, if you are able, please turn your cameras on. It's very lonely and sad in the dark. I would like to see your faces, right? It's always so pleasant to see your faces, so please. You have too much time on the exam, so much time that it's a take-home exam, as I mentioned, right? You have too much time on the exams I give, but on the final you will have just 2 hours. Good. So you have too much time on those exams. So much time you can easily cheat on it. But if you do, there would be traps. I'm not going to tell you. Maybe I will not know. Right? And maybe I will. But some people thought I will not know last semester, and they were wrong. I did. So decide if you want to try me, see if I can figure it out. Okay, good. So you think you're going to be clever. Good, we'll see. We shall see. All right, so today we begin a wonderful new topic, trigonometry. No, guys, you understand what I'm talking about, right? It's just much more relaxed than you imagine, right? You understand what I'm talking about. You understand, hopefully, what is my goal, right? And if you do, then we're on the same team there. So we are ready to talk about trigonometry, guys. And we are actually going to review trigonometry from the very, very beginning. So tell me, please, how many degrees are in a circle and why? So first, how many degrees? 360, amazing. 360, everybody spits it out. Everybody knows that a circle has 360 degrees, apparently. Now, why? Exactly, Francis. The Babylonians were fond of 60, arbitrary reason. But why is it one for revolution? So if you look at 360, I'll mention that below. I'll just mention a few things about numbers. So Babylonians counted in terms of the number 60. Okay, so what was the reason? I cannot tell you beyond that, but whatever that reason, it's arbitrary to the circle. Okay, maybe it had to do with some with how many days they imagined but again, I'm not sure they imagined the sun, the Earth going around the sun. What? Maybe it's a sort of calendar that they imagine the year is 360. Who knows why exactly, right? But they had a base 60 system, and our base is seems more natural to us because we have 10 fingers. So our system is 10. Now, what is base 10? What is base 60, guys? It's nothing other than this idea that you can encode it as a polynomial. There's much to do with polynomials. Okay, so if you are using base x system, then the number is an x to the n plus an minus 1 x to the n minus 1 all the way to a0, where ak is between 0 all the way to x minus 1. So if, for example, if I use base 10 system, guys, it means that I describe numbers in powers of 10. So what is 153? It is 1 times 100 squared plus 5 times 10 to the power of 1 plus 3 times 10 to the 0. You understand what I mean, guys? This is just what you do. You bundle into units until you get 10. You bundle in tens until you get 10 bundles of 10. Then you just bundle them together into 10 squared, and so on. Again, guys, Robert, Humira, Marie Carla, Karen, Francis, Elisha, would be very nice to see your faces. I feel like my vision is fading. I mean, you know, it's very scary. Did I have a stroke or something? Great. Great. Nice to see you, Christine. Thank you for appearing. So, for instance, the number 33.533 is the same as 3 times 10 to the power of 1 plus 3 times 10 to the 0 plus 5 10 to the minus 1 plus 3 10 to the minus 2 plus 3 10 to the minus 3. Right? Now, how do you write 153 in base 9, guys? So if it's base 9, I use powers of 9 square. So what is that number, 153 base 9? It is, if I convert it to base 10, it means what? It means 1 times 9 squared plus 5 times 9 plus 3 times 9 to the 0. You see, this means 9 squared, 9 to the 1, 9 to the 0. And if I write it down, it's the same as 129 in base 10. If I convert 153 in base 6, that means into base 10, that's 1 times 6 squared plus 5 times 6 to the 1 plus 3 times 6 to the 0, which ends up being 69. Good. And if I have 360 in base 10, look what happens. That means I have 6 times 60 to the power of 1 plus 0 times 60 to the power of 0. I converted, basically I took it as base 10 and I want to convert it to base 60. And what do? I select the biggest power of 6. 60 squared is too much, so 60 to the power of 1. How many copies of 60 to the power of 1 can I have? I can have 6 copies. So it's 6 times 60 to the 1 plus 0 times 60 to the 0. So 360 is 60 base 60. I hope you understand what I mean, guys. 60 base 60 means simply the first number is 6 times 60 to the 1. The second number is 0 times 60 to the power of 0. That's how you convert it, okay? So from the Babylonians, we retained the way we measure time. So 1 hour is 60 minutes. 1 minute is 60 seconds. You understand? We kept that measurement in Babylonian time. So the clock, as you can think of, is you can see this is basically what do degrees and how do they measure it? What are degrees, guys? In essence, do you by any chance have an idea? A very simple explanation of what are degrees and what are they supposed to measure. Yes, and what is an angle? So degrees are measuring angles, and what is an angle? Exactly. So it's a sharp tone in a shape. That's a good description, Robert. Well, it's a measurement of the wedge. So an angle, guys, is, in my mind, it is just the measurement of how sharp is a wedge. So this is sharp, this is less sharp, this is more sharp, right? So the angle is the measurement of sharpness of a wedge. And how do we measure sharpness? We can take a standard unit of sharpness, which you decide to be the degree. And how do you make that standard unit of sharpness? Very simply, guys. Take let's say take a pizza and cut it into 360 parts, equal wedges. So a Babylonian pizza is sliced into 360 slices. And then place any wedge. Any wedge measures some number of slices, at least so we hope, right? We can say slices or half of that slice. So how many Babylonian slices are in which wedge? So this wedge is 3 degrees. That means it's 3 slices sharp. If this were the degree slice, then this is 1, 2, 3. It's at least 3 slices sharp. This one, although the picture is bad, this one is sharper because it has a smaller, it fits fewer Babylonian slices. You understand? The smaller the degree, the sharper is the object. Good? Now, of course, there is nothing natural about cutting the pizza into 360 slices. In other words, there is nothing about the circle that tells you cut me into 360 parts. You could have cut it into other parts. So what is an American angle measurement? What's an American pizza? How many slices do we produce when you go to buy a pizza? So you have 8, right? So you can say the circle is 8 American degrees and 360 Babylonian degrees. You understand? Now, can you tell me by any chance how much is, how many Babylonian degrees are in 1 American degree, please? If I take 1 American degree, how many Babylonian degrees are in it? Very good. 40 what? 45. How do I know, guys? Cut the pizza into 2 parts, right? Half a pizza, you have the diameter, it's 180 Babylonian degrees. Do you agree? Cut it again in half each of them. Now 90 degrees. 90 degrees make 4 parts of the pizza. Now cut each of them again in half. You have 45 degrees, right? Cut it in half, then again in half, then again in half, and you get 8. Right? So you cut in half, it's 180. Cut again in half, it's 90. Cut again in half, it's 45. Which means 1 American degree, 1 American slice is equivalent to 45 Babylonian slices, or what we call degrees. Clear? Nothing very hard here, I hope. Now, there is a natural measurement for angles that you use in calculus. Natural measurement because it's a property of the circle, rather than cutting the circle into 360 parts is not a property of the circle. You can do it, but it's not. What a circle is not asking you that. It's not an intrinsic property of the circle to be cut into this many parts. But a natural measurement comes from what's known as radian measure. And what is the radian measure doing? I can show you an animation, guys. Radian measure is this idea that take any circle, take any pi, and what you would observe is you would observe the following. You would observe that the circumference of the circle is 2 pi r. Archimedes found it, 2 pi r, where pi is 3.14. What it means, guys, is that the circumference, if you measure in unit radius, if you measure the circumference using radius length, you will find that the circumference contains about 6 copies of the radius. 6.2 copies, or a little more than that even, 6.28 copies of the radius. Do you understand? I try to illustrate it in this picture. So here, I measured the radius in inches. So here is one radius in inches, and then I fold the radius along the circumference, and you see here is one, 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 here is one. You count approximately 6 radii. If it's a bigger slice, you count approximately, they are longer in length, but again, there is this big radius, which is 2 inches long, but the circumference of the red circle is about 6.28 radius lengths. Do you understand? So with degrees, we speak about the slices. With radians, we speak about the crust. And of course, because there is bigger crust or smaller crust, we measure the crust always in terms of the length of the radius. How much crust per radius do we have? You understand what this picture is showing you? I mean, the red crust is longer than the blue crust. But what's true about both crusts is that if you take the respective radius of that circle, you would see that the crust contains exactly exactly 2 times pi radius lengths. When you say 2 pi r, you just mean the measurement in the units you're using to carry it out is 2 pi multiplied by the length of the radius. So if I measure it in inches, the blue circle measures 2 times pi inches, and the red circle measures 2 times pi times 2 inches. But in each case, the measurement is about 6 radius, 6 radii length. Good. So this you can prove, but I mean, you can just take it as given. That's an Archimedean property. I can show you at some point if you want to. Here it is, guys. If I were to unwrap the circle, if you see, if I were to unwrap this blue circle and lay it on the x-axis from here onwards, I will see the measurement is going to be 6.28 something. That's the circumference. Okay, so smaller crust means sharper angle, right? Smaller crust, sharper angle. Larger crust means bigger angle. So I'm using the crust to measure the angle instead of the number of slices. And the reason that it's good, guys, it's intrinsic property. Do you understand? It's a property of the circle that the radius can be folded around the circumference about 6.28 times. Do you understand me? Are we together? Now, so you would, once in calculus, you will see the formulas are natural and easy when you do radian measure. What you do in calculus, you always prefer radian measure. The formulas come out nice. So my question is, of course, well, can you compare degrees and radian measure? So how many radians are in 1 degree? Here is, guys, again, I can show you, this is my picture before we go there. You think of a pizza, right? So this is supposed to represent 2 degrees. So you can see there are 2 slices here. And this is the circumference of the slice measured in unit radius, you understand? So I always measure it in terms of the length of the radius. If I make my pizza bigger, my radius gets bigger. Right, but the measurement will then be invariant. I don't measure it in inches, I don't measure it in centimeters. I always measure the circumference by taking out the radius and folding it along the circumference. Does it make sense? So this angle S is radian measure. That's very useful, guys, because that's what you use when you're driving a car, for instance, right? Your wheels are turning and it converts the turning of the wheel into linear motion. So your odometer tells you how far you traveled based on the size of your wheel, as measured in well, you need to know what it is in radians. So you can see that the question is, of course, in this situation, you see that 2 degrees. This is the slice containing 2 of the Babylonian slices, and S radians means the crust that is for the combined Babylonian slices. All right, guys. So now back to that question: how many radians does 1 degree contain? And what does this mean, this calculation? Yes, Christiana, that's good. And Humira, very good. Humaira, I'm sorry. Would you also, we will try to explain this idea. Very important, guys. Well, in terms of anything, it has to be, I want you to have a very, very clear notion of what's a degree and what's a radian and how they're related and why one is natural and the other one is man-made. So I only saw a few people respond, guys. How many degrees are, sorry, how many radians in 1 degree? What am I asking in terms of the pizza? No, Francis, you confused between American degrees and Babylonian ones. Good. Pi over 180. Now, how do we know that, guys? Very simply, 360 Babylonian slices carry 2 pi radians. Do you understand what the 2 pi means, guys? In other words, if you look at any pizza, circular pizza, and you cut it into Babylonian slices, they combined carry the combined number of slices is 360, and they carry the length 2 pi radians. You understand what? I don't need to mention what's the size of the radius. 2 pi radius lengths. Are you understanding me, guys? You understand the invariance? If I measure it in inches, naturally the crust of a bigger pizza is going to be longer than the crust of a smaller pizza, but not in terms of the radius, right? If I take the radius of the pizza and I create a meter out of the radius of the pizza and I fold that meter tape around the pizza, I will find that the circumference will always be measuring 6.28 something, basically 2 times pi precisely. Good. So how much is, so if 360 identical twins bring together 2 pi crust, how much is each twin carrying? I think of pizza slices as twins, as you understand, right? And each of them naturally carries 1/3 360th of the full quantity. So 1 degree, and I draw 3 lines because you see, some people can be confused. I remember even myself in high school, I thought, you say pi is 3.14. So how can pi equal to 180? Right? So I am talking about correspondence. 1 degree carries 2 pi over 360 or pi over 180 radians. Good? Do you understand, guys, that pi is not 180? It's just like saying 1 kilometer is 1,000 meters. It means that each kilometer contains 1,000 meters. So each degree, each 1 Babylonian slice contains a crust that is pi over 180 radius lengths. Are we all clear what is pi over 180, what it means? And 180 Babylonian slices contain approximately 3.14 radius lengths. In other words, if you took the crust and flattened it, it will be approximately 3.1415962, I believe, or something, or 926. Yes, 926. Good. Now, if you understood it, please convert. What is 2 degrees? Tell me what's 2 degrees, what's 180 degrees, what's 120, 60, 90, 45. Begin with 2 degrees. Quickly tell me what's 2 degrees. Yes, Christina, yes, Humaira. And what about the rest of you? Good, wonderful, wonderful, good. Now, 180 degrees is what? I was mentioning it myself. 180 degrees is pi. Now, what is 120 degrees? Exactly. 2/3 pi. 2/3 pi. 60 degrees, 90 degrees, 45 degrees, you're all clear. Anybody needs elaboration on this, guys, or you understood? Very simple. If you think of degrees, think of the slices. If you think of radians, think about the crust. And make sure that you measure the crust in unit length, that's the radius. So if the pizza is longer, the radius is longer, but it's always unit length. Right? You just adjust. And here we have it all. Now, would you tell me how many degrees is one radian carrying? One radian carries how many degrees? Would anybody also tell me, before you answer this, what is 1 radian? Give me a sense, or give me a picture of what's 1 radian. No, it's not, definitely it's not half a circle. Yes, Giovanni, but an impression, what is 1 radian? What do you do? 1 radian is no. So 1 radian is what, guys? So first, very simply, just imagine you have a very flexible rubber meter, and 1 unit is the size of 1 radius. What do? You place it at the edge of the pizza, kind of like this. If this is 1, then you take this piece out, you fold it around the crust, and this slice is a slice of 1 radian. So 1 radian is approximately 1/6, a little bit less than 1/6 of the full pizza. It's a little less than 1/6 of the full pie. Are you clear? because 2 pi radians or 6.28 will make the full pi. So now, again, you would be converting. Please convert. Please tell me what is, again, sorry if you already did. Tell me again what is 1 radian in degrees. Convert 1 radian to degrees, please. No. Okay, good, Christiana. Good, Humira. 1 radian to degrees. When I say approximately 1/6, guys, of course you understand it's approximately. I want you to give me the precise description. So here it's very simple, guys. 2 pi radians bring together 360 degrees, which means 1 radian brings 360 degrees divided by 2 pi, or 180 over pi degrees. So when somebody said 60, they were not terribly wrong. I mean, maybe you meant an approximation, right? It's 180 over pi is roughly 57.296. So 60 is kind of close, and maybe that's what you meant, right? You gave me kind of a sense of what it is, but it's less than 60 because the circumference is containing more than 6 radii. It's 6.2 something. Good. Now tell me, please, here, guys, I want you to tell me how many degrees are in this sector. You see this picture? This is 3 inch long. This is 1 inch long. I want you to tell me how many degrees. By the way, what am I asking? I'm asking how many times can you place a Babylonian slice in it? How many Babylonian slices fit in this wedge? Clear? So how many degrees are in this wedge? Giving this information, please. Y tangent. Don't try, guys, to use some formulas or memory, right? Just use your logic. What am I asking, first of all? Can you, if you cannot right away get to degrees, can you tell me how many radians is the sector? Okay, Christiana, you are doing it perfectly. Yes, good. Think about it, guys. I only see 2 people here that do it fast. Okay, where are you confused, Francis? Before you try to get something, just ask yourself, what is that radian supposed to measure? What am I really doing? So I have a ruler that tells me that the radius is 3 inches long. Do I need inches? When I report radians, I am reporting what? I want to know how much is this arc measured, how much the crust is measured in radius units. This is not in radius units. Inches here are not radius units, right? If it were, if the circle were 1 inch long, it would be radius units. But the circle is 3 inches long. So radius units, 1 radius is 3 inches. Good, 60 over pi, right? Radius is supposed to be measured in, well, so basically, if I convert this, if this is 1 radius, how much is this in terms of radius? This is 1/3 of a radius. Do you agree? If this is 1 radius, then this is 1/3 of a radius. Is that clear? Now, if this is 1/3 of a radius, then I am converting 1/3 radians. But this is 1/3 radians. So how much is 1/3 radians? Well, I remember that 360 is 2 pi radians, which means 1 radian is 180 over pi. And I need not 1 radian, but 1/3 of that. So 1/3 of 1 radian will be 60 over pi degrees, or 19.099 approximately. Right? It's not. You understand, guys? What you see? It's very clear if you're very clear about what you're measuring and what you're communicating. Right? You are trying to describe how sharp is this wedge. So when you do that using radian measure, you are doing that in terms of arc, in terms of the crust. You understand? You tell this wedge is sharp by mentioning how big is the crust. But you understand that if I have a very big pizza, maybe it's very sharp, but if I make a bigger pizza, the crust will be longer. So I have to report it in an invariant fashion. And the way I do that is I measure the crust always in terms of radius length. It's easy, right, guys? You understand why in radius length? You make a bigger slice, longer slice, if the wedge remains at the same, if the wedge remains as sharp, that is not going to alter the proportion of the slice relative to the pi. So I'm measuring the proportion the crust is making to the pi. All right. So what does the 90.099 mean, guys? Could you tell me in a very simple language? 19.99 means what? Don't use the word degrees, whatnot, right? I want you to show me that you see what it means. Very good, Christiana. Thank you so much. Precisely what I have in mind. You see, guys, 90 slices, Zakaria, not in 1 inch precisely. You're close there, right? Because inches are kind of arbitrary here. Just in that particular sector, it's the same as 19 Babylonian slices. And you understand, guys? So it's very, very visual. It should be like this. All clear? Now, let's talk about polygons and angles, guys. What is the sum of angles of a triangle? Okay. Okay, but more people should write something. You, of course, know what I'm going to ask you. Do you? You don't know what? Whoa, here, Giovanni does. Of course, right? Do I care that you memorized it? I do not. Why? Why does a triangle have 180 degrees? The sum is 180 degrees. By the way, in radians, it's pi. Do you agree? 180 degrees means pi. Pi radians. We are going to try to think in radians, guys. So I prefer when you report it in radians over degrees. Did you understand, guys, why radians are natural? Did I explain that? It's a property of the circle. You understand? So for instance, to say that my finger is maybe 2 inches long, it's not natural, because why do I need to measure it in terms of inches? But to say that my finger is as long as my nose is natural, because it's an intrinsic proportion. You see, like, the finger, you can compare it to other part of myself. It's basically a property of my body. Measuring it in inches is not a property of my body. That's why radians are natural. Are you clear? Now I'm asking you, why does the sum of angles add up to 180 degrees or to pi radians? Any ideas? It's, by the way, not a simple question, guys, and very important. Gauss had a theorem known as Theorema Egregium, I think, the grand theorem. He discovered that if space is curved, the angles of a triangle do not add up to 180 degrees. If they add up to less than 180 degrees, then the space is hyperbolic, and if it adds up to more than 180 degrees, the space is spherical. So by studying the properties of physical triangles, and whether or not the angles sum up, you actually understand if your space is curving. Right? So pretty interesting things happen there. So I'll show you a very simple way, guys, to understand. I hope it's a simple way to understand why the sum of the angles of a triangle is equal to pi, or to 180 degrees. Are you ready? In high school, I thought about it. I came up with a different proof. This one is better than the one I came up with, but I thought everybody knows it then, and I kind of kept it a secret. You know, I thought if I mention to anybody, I'm thinking why the angles add up to 180 degrees, they would think, well, I'm stupid. Because I thought everyone knew that. So here we go. Guys, have you ever walked around a park? Any park? Right? Do you like to take long strolls? Do you ever walk around? Yes. Now, if you walk around the park, forgetting about the distance you travel, how much do you turn? If you just only look at your orientation, where you can tell it by just where you're looking, how much do you turn once you complete your walk? Any ideas? You walk in one direction around the park, how much do you turn? Look at it. You can imagine attaching a marker to your nose, and you know that you made a full revolution. Exactly, Barbara. You made a full revolution. Right? A lot is not good, guys. I mean, how much do you turn? You made a full revolution once your nose is pointing in the same direction again. Do you see that? We're going to use that to understand why the sum of angles is pi. Now let's suppose we carry it out, guys. Look at it. So here I begin to walk along some arbitrary triangle. Are you with me? This arbitrary triangle has inner angles A, B, and C. And so I'm just paying attention to how much I turn on the outside. Look at it. So you see my red dot? I walk up straight. I'm not turning. Whenever I make this motion up, I'm not turning at all. Do you agree? Until I reach this vertex, then you can imagine walking a little bit farther and turning. I turn some angle A prime. Are you with me? I don't know the value of it, but I just know I turned an angle A prime. Right? Because my nose, my pointer is no longer in this direction. It's now along the direction labeled as motion 2. Now I continue walking over here. And again, I make another turn B prime. Yes? And then I continue walking and make third turn C prime. Do you see that I'm now pointing in the same direction? You see, I was turning always in the same direction, and now I'm pointing exactly the same way I was pointing before. Yes? It's amazing. Look what's happening, guys. So how much have I turned? I just drew another picture here. Do you see that I turned exactly 2 pi, or 360? because I made a full revolution. Look at it. If I don't keep track of how much I move, I just keep track of how much I turn, I must have turned 360 degrees, 2 pi. Do you see that? It's very important for you to see that. Yes or not? Good. A few people say yes. I mean, I need you to all understand it, guys. Very important principle. It's just keep track, guys. You see, when you walk straight, doesn't matter forward or not, unless you are turning your head. You don't have to turn your head until you reach to the corners. You don't turn. And the idea is this, guys. Whatever you walk, you turn, turn, turn. If you are, again, if you're turning in the same direction and then you end up pointing in the same direction you started with, you must have made a full revolution. Do you understand that? As you walk around the spark, you'll make a full revolution. Do you see that? The degree is equal to slices, but forget about here. I need you to notice that when you walk around something, you're not walking in a circle, but your amount of turning ends up being a full turn, 360. Yes? The sum of the angles, how much you turn, must be 360 because here it is. I drew a picture for you, but you can see it over here. Now, look at it. We have A prime and A, we have B prime and B, C prime and C. They are complementary angles. Now, because they're on a straight line, they are half of a circle. So A plus A prime is 180, or pi. B plus B prime is pi. C plus C prime is pi. Clear? So what do we get, guys? We see that if I add them all together, if I add, I do not know I don't know A or A prime, but I know their sum is pi. I don't know B or B prime, but their sum is pi. C and C prime, their sum is pi. So if I add them all together, look at it. If I add them all together, I get 3 pi. Are you clear why? If I add A and A prime plus B and B prime plus C and C prime, I get 3 pi. Because each of them is pi. Now I can regroup and isolate the primes, the outer angles. The outer angles, I know they add up to 2 pi. I don't know individually what they are, but I know together they must add up to 2 pi. Clear? And so what do you get? You get that A plus B plus C is 3 pi minus 2 pi, or pi. Isn't it amazing? Very easy proof, and now I see why a triangle has inner angles adding up to pi. Do you understand it? We're going to see if you understand that proof in one moment. Here, guys, is your next challenge. This is a quadrilateral, or whatever it's called. It has basically 4 sides. I want you to tell me what's the sum of inner angles. And not maybe you notice a pattern, but I want you to actually reason the way I reasoned for the triangle and tell me what's the sum of the inner angles. Thank you, Christiana. Thank you, Homira. Thank you, David. Very good. Thank you, Joseph. Faeza, thank you. You just have to understand the idea, guys, right? Once you get it, it's very simple. Once you see it for the first time. Jahin, wonderful. I see a few of you are getting it. That makes me very happy. All right, a few more. One more minute and we'll do it together. Thank you, Giovanni. Not wonderful. What do you mean? Because you know the sum of the angles in a trapezoid is 360. Well, it's, I forget what people call shapes. I mean, you can just see it from scratch, not just for trapezoid, but for any quadrilateral. Right? It has nothing to do with a particular shape. It's always true.
Well, yeah, trapezoid, square, rectangle, it's all the same.
But all of them, you don't need that. You don't need to kind of remember or know it. You can just, you see this argument that we just had should convince you that it's true for any quadrilateral. That's the point. Like we did for the triangle. Are we ready, guys? So this is the idea. Do you see that I can start moving here? Look at it. Let me start moving here, and I make A prime turn. Move here, make B prime turn. Move here, make C prime turn. Move here, make D prime turn. What's the sum of the outer angles, please? What's A prime, B prime, C prime, D prime together? Type in the comments. 2 pi. Very important, guys. Do you all see that the sum of the outer angles are 2 pi? This is just because I realized that I turn in the same direction. I don't go back. I always turn in the same direction. And if I turn in the same direction and I end up pointing where I used to be, that means I made a full revolution. That's what we use here. That's the insight. Are we clear on it? Full revolution. Now, what else do I know? I know that the sum of inner and outer angles, because they lie on a line, they are half a circle. So that's pi. Good? So what do we have? We have pi plus pi plus pi plus pi. We have 4 pi. Altogether, we have 4 pi. And subtract from it the sum of the outer angles, it gives you 2 pi. The outer angles add up to 2 pi. So add up inner and outer angles, all of them together, you get 4 pi. Subtract 2 pi, you get the inner sum. You understand? We know the outer sum and we know the total sum of inner and outer, so we can get the inner sum. Make sense, Angela? So I just right away say it's 2 pi. Here is another quick question, guys. So we have now 5 vertices. Very quickly tell me what's the sum of inner angles of a polygon having 5 segments. Beautiful. People already see it. You see, we didn't only learn it for triangle, we did it for all sorts of shapes. We right away can figure out the sum for all shapes. How do we do that? We look at all the angles we have and multiply that number by pi. So here I have 5. 5 pi is the sum of inner and outer. And the outer ones will add up to 2 pi. So then just subtract 2 pi. Does it make sense? 5 times inner and outer, it's 5 times pi. Subtract 2 pi for the sum of the outer angles. So you get that the inner angles must be 3 pi. Very simple. Yes, guys? As long as you understand why the outer angles add up to 2 pi, that's very simple. So here is the calculation. And of course, what's going to be the sum of a polygon that has n vertices? In general, like 3, 4, 5, 6, 7, n vertices. If it's a million vertices, right? So that's what the n is supposed to do. Tell me what's the formula for n vertices? It's not n pi, no. It's n minus 2 pi, Humira, correct. It's n times 2 pi. It's n times pi minus 2 pi, right? It's n times pi minus 2 pi. So it's n minus 2 pi. Are you with me? Good. Here is that calculation. Again, guys, if you think it's a boring thing, then you're not seeing the progression of it. You see, as it happens, this has to do. I mean, eventually, if you're interested, let's say, what is my favorite thing to do, guys? If I could, I would travel back in time. Right? That's I'm obsessed about moving back. If I could. So those results, they relate to time travel because they relate to curvature of space-time. So studying this lowly triangle in the sum of its angles relates to the nature of space and time. And leave, travel back and do what? Although there is a nice poem and they say, for fortune or unfortunately, the truth is simple, never return to places that you've been to. It's in Russian. По несчастью или к счастью, истина проста. Никогда не возвращайся в прежние места. But I want to return. Now we're going to talk about measuring areas and volumes, guys. So area and volume are just trying to describe the size of space in terms of some unit segment. So if we're studying two-dimensional space, the natural object to use for that is the square. Why the square? Because the squares tessellate very well. Tessellate means that you can adjoin squares like tiles and they cover the whole of space if it's flat, right? So this is an example of a tessellated space. And when you say the area of this red rectangle is 3 times 2 or 6, you're just saying that this region is equivalent to 4 unit squares, sorry, to 6 unit squares. Clear? What do you do here when you say length times width? You just multiply. When you multiply, you're just counting. You're saying 1 row contains 3, and 2 rows contain 3 plus 3, and 3 rows contain 3 plus 3 plus 3, and onwards, right? So that's where multiplication of length times width comes around, because all you are doing is counting. How many squares, how many tiles are to that space? Good. So area is area of a rectangle is length times width, or height times width, or whatever you call it. Okay, so can you tell me please what is then the area of the triangle? You can begin with a right triangle. What's the area of a triangle if the area of a rectangle is width times height? Exactly. Now, why 1/2? What is the 1/2 about? You just multiply by 1/2. Why is there 1/2? Half the rectangle. Exactly, guys. Could not have said it better, Humira. You see, guys, a few people, they're understanding. They're speaking the way I want them to speak, right? They're seeing pictures here. Right? You're not seeing letters. You're supposed to see pictures. You're supposed to see why this is obvious. So here, if I take a right triangle with width W and height H, the area is W times H. In other words, this rectangle contains W times H copies of unit squares, if it's integers. I mean, if it's fractions, it's a similar thing. And the 1/2 is because we take half of it away. Good. Now, if I have an arbitrary triangle, I can do this, guys. Here is somewhat an arbitrary triangle. Do you see? It's not a right triangle. What's the area of this triangle? Well, suppose I know the height. Suppose that the height is basically, it's a line perpendicular. I just take this corner and I draw a line perpendicular to the axis generated by W, and I join them. You can see what it is. So what's the area? The area of this triangle would be 1/2 W plus W dash times H. This red region I don't know, right? Minus the this red region. It's this big right triangle minus the red right triangle. Do you agree? And when I carry that calculation, what do I get? I get 1/2 W times H. So the area of a triangle is always, no matter whether it's right or not, it's always 1/2 base times height. You understand? Robert, today you're invisible. I was thinking, yes. Who am I not seeing? Robert, that's right. Now, guys, we come to the Pythagorean Theorem. Yes, I'll be happy to, Robert. Pythagorean Theorem, guys. All of you have heard of the Pythagorean Theorem, correct? Do you know that Pythagoras, you know the way he died? Do you know how Pythagoras ended up dying? No? Really, it's strange. Pythagoras, you know, he was a sect leader, and he was afraid of beans, for whichever strange reason. So afraid of beans. And once there was an angry mob chasing him, and he could have escaped, but there was a cart of beans, so he decided better to die. So they basically tore him apart, apparently. Right? He's a very weird fellow. I do not know why, Francis. Here now, if Francis is asking why. Well, good. I get you to ask why. That's precisely what I am asking all my life. Well, is that real? Guys, it happened so many years ago. There are many legends, but I'll tell you other legends that might or might not have been true. It's hard to say. Pythagoras lived a long time ago. So who knows? You know, I'm not sure what happened yesterday. What happens today, one is not sure what's the truth and what's not. What's a rumor? What's misinformation? So how can I tell you what was real thousands of years ago? So here is Pythagorean theorem. If you take a right triangle and it has legs A and B and hypotenuse C, the relationship between them is a squared plus b squared is equal to c squared. Yes? Now, can you guess what question I'm going to ask you? I'm sure you can. I'm predictable. Exactly. Why? Right? I mean, it's not a hard theorem at all. At least there are very easy proofs, and one easy proof I will present to you. So just before I do, guys, could you type in the comments, do you know a proof? At least one proof? Or you are not aware of any proofs? Francis, you're saying you know a proof. Well, Robert, I just believe through faith. That's nice. We have a lot of religion majors, I guess. Theologist. What do you mean addition proof? So here is a simple proof, guys. I think very simple. So all of you have to know it. So take a right triangle. Look at it, guys. It's even in the proof. You see, this means a squared, it's a square of sides A, and b squared is a square of sides B, and c squared is a square of side C. The relationship is that the sum of those squares, the sum of the squares built out of legs is equal to the square on the hypotenuse. There are many methods. There are like hundreds and hundreds of proofs of the Pythagorean theorem. I'll show you one that I find especially easy. Good. So what you do is, guys, take one such triangle. Here it is, A, B, and C. I just picked one of them. Ready? And then what you do is you make 3 copies of the same triangle, and you place those copies by rotating them. Do you understand? Take this copy and adjust so that B is after A, and after B there is A, and after A there is B. You rotate them basically by 90 degrees each time. You see, take this, rotate by 90 degrees, rotate by 90 degrees, rotate by 90 degrees, and you form that figure. Are we clear? Easy so far, yes? Now, you can prove if you want to, if you don't believe me, but you can see that what you generated is a square. Am I right? It's a square. The big square is of sides A plus B. A plus B, A plus B, A plus B. Do you agree? So my goal is to measure the inner square. So the inner square is simply C squared. It's C multiplied by C. The inner square is C squared. I can also get the inner squared by taking the big square and removing the areas of the 4 triangles. Clear? Just a simple correspondence. So look what happens. So C squared is equal to A plus B squared minus 4 areas of the right triangle. What's the area of this triangle? It's 1/2 A times B. So what do we get? We get C squared is A plus B squared minus 4 times 1/2 AB, which is, if I expand this, it's A squared plus 2AB plus B squared minus 2AB, which gives me A squared plus B squared. Are we together? Isn't it easy, guys, right? Very quick and easy. Correct? You understood my proof, guys. I'm not just, that's why I'm slowing down. I want to be sure that if I asked you this thing, not on an exam, but in person, in an interrogation, you would easily be able to construct it, right? Just take a triangle, a right triangle, rotate it by 90 degrees, make several copies, rotate by 90 degrees, form the big square, and you see that the small square, C squared, is equal to the big square minus removing the 4 triangles. Mariam, where did I lose you? Look at it here. You see that A plus B squared is the area of the big square. If I remove from the big square the areas of identical triangles, I get the area C squared. Do you follow, Mariam? Okay, and what's the area of the small square, of the triangles? It's 1/2 A times B. 1/2 A times B times 4 is the area of all 4 of them, which is just 2AB. So I take A plus B squared minus 2AB, and I get C squared. Because I take big square minus triangles gives me the small square with side C. That's as simple as it gets, correct? So now we see why the Pythagorean theorem is true. So guys, this Pythagorean theorem was something very important and secretive in the Pythagorean doctrine, which stated all is number. They had this strange saying, all is number. What do they mean by all is number? So you can ask this question, guys. When you ask how tall is somebody, how long have you studied? How much do you weigh? How fast are you driving? Is the future determined? Is there such a thing as cause and effect? Is time travel possible? Those questions relate to the question, first of all, do they even make sense, those questions? The Pythagoreans believed that you can unify, scientifically, you can unify different aspects, different features, in particular in geometry, through measurement. So for example, I can measure this pen in inches, correct? That's what you imagine. When you imagine that, it means that I can communicate the length of this pen, the space within this pen, in terms of the space markings on a ruler, on an inch rule. you know, on a ruler with inch marking, so to speak. Sorry for my. Understand? I will try to show you what actually happened and what secret the Pythagoreans had. First of all, guys, do you believe that this communication is possible? Do you believe in this universal communication? They thought all is number. It's, for example, there are things that are attracted by gravity, and I can compare several things that are attracted by gravity. Do you believe in this ability to compare between different things? All is number and money too. That's good. All right, so here is the situation, guys. So how many centimeters in this line segment? You see, I see that it's 1 centimeter, 2, 3, 14, and there is a small segment. So maybe that small segment is not quite a centimeter, but maybe it's 4/10 of a centimeter. So this is 14.4 centimeters long. So the Pythagoreans believed in fractions. Do you understand what I mean? When they say all is number, it's a sort of carpenter's type of idea of measuring. Because I can say how many centimeters is this pen, plus maybe a fraction. So how many integer centimeters, then maybe a fraction, maybe 1/10 of a centimeter. There was a way, very technical, where you can divide any segment into equal parts. Let's say I can take a segment and divide it into 20 equal parts, or 7 equal parts, or 19 equal parts. You understand? So they could manufacture fractions. It's not easy to divide, guys. Think about it, right? Imagine that you have to fold an envelope exactly into 3 equal parts. That's already not so easy. Half, kind of easy, right? But imagine you have to cut it into 17 equal parts. How are you going to do that? And there is a geometric way, a very simple machine that would do that precisely. And the Pythagoreans knew about it. They carried such measures. It was necessary for architecture. It was necessary for carpentry. Clear? You should watch maybe how castles were built. You might find those things interesting. Those ideas were always used. So if you are if you're a carpenter or some sort of skilled craftsman, you would have to know about those fractions and how to generate them. Now, the Pythagoreans discovered something which later became known as irrational numbers. Okay, and what it is, I'll try to explain to you guys. So first of all, here is a triangle of sides 1 and 1. Yes, it's triangle of sides 1 and 1. What's the length of the hypotenuse? Please type in the comments. It's not 2. The length of the hypotenuse, what is that? You can use Pythagorean. No, it's not 4. My God, what's going on, guys? Square root of 2, precisely. Square root of 2. Why is that so? Because look at it, guys. C squared, the Pythagorean theorem allows us to relate not c but c squared to the sides, correct? So we see that c squared is equal to 1 squared plus 1 squared, but 1 squared plus 1 squared is just 2. So c squared is equal to 2, and c is root of 2. Is there such a number? What do you think? Yes, there is such a number, you're saying. So 2 people just responded. The rest are, where are the rest? Are you with me, guys? So you're all saying, yes, there is such a number. Now, if there is such a number, maybe it's a, what is it? Is it a fraction? Right? Fractions we understand, correct? Well, when Humira, you say an irrational number, that might be a meaningless word. What is an irrational number? Right? It might be just a bad labeling that means nothing whatsoever, right? So fractions, do we understand what fractions are, right? You understand what it means to take the segment and cut it in half, or to cut it into 7 parts. Like you understand why this is kind of very understandable. If I want to describe this length of this line segment in terms of centimeters, it's 14 centimeters plus a fraction, plus 4/10 centimeters, because I can cut the centimeter into equal 10 parts, into 10 equal parts, and take 4 of those parts. And this way I produce what I call numbers, fractions. I understand segment and I understand some part of that segment. I can communicate the length pretty well this way. Are you understanding? It's a very good communication. You're saying it's 14 centimeters plus 4/10 of a centimeter. So cut the centimeter into 10 and give me 4 of them. So I have this way of communicating the length. So now let's try to see, is this similar? Can I, all things that I can communicate this way can be written as some integer m divided by some integer n. Do you understand, guys? Because like I did with 4/10. 4/10 is a fraction. I could take 14 and add to it, and I can make it 72/5. So Pythagoreans understood only fractions. Right? Let's see if you understand anything better than that. So, but fractions still represent a part of the whole, but √2 isn't part of the whole. Well, that's the question we're going to investigate. Something a bit difficult, guys, but I hope you will find it interesting what I will say to you. So here is the situation, guys. So m/n, this number c, is √2 is something you press it in the calculator spits numbers out. So maybe that's why you're saying there is such a number. Good. But let's try to calculate what sort of, whatever the calculator writes down, guys, it's a several decimals, which makes it into a fraction. The calculator gives you a fraction. Are you clear? Because no matter how many digits you're seeing in the calculator, that's a fraction. It's basically what is this number, guys? What is, for instance, 1.517? This is the same as 1 plus 517 over 1000, which is a fraction. So no matter how many digits you have, your calculator is giving you a fraction, correct? So when you ask what's √2, you're getting a fraction. Now, is √2, is there a number that will be giving you 2 when you square it? So let's suppose this number is a fraction of the form m divided by n. You see, the reason I say m/n, because I do not know what m and n are. So I'm just supposing that there is going to be a fraction that works. I just don't know what are the exact numbers. So I just use m/n to say there is some integer on top divided by some integer on the bottom. Are you with me? I cannot say numbers. I cannot say 2/7. I don't know what those numbers are. I'm going to try to see if I can do something here. So suppose it's m/n. That means that I can, of course, carry them in simplest terms. I can simplify m and n, divide anything so that the greatest common divisor of m and n is 1. So for instance, 3/6 can be reduced to 1 and 2. And now nothing divides both numerator and denominator other than 1. Correct? You understand, guys? m/n, I'm assuming they're in reduced terms. In other words, whatever divides n divides m must be 1. That's the only thing that can work. So then I take the square of that number. So 2 equals to m/n squared, which is m squared over n squared. And if multiplying by n squared on both sides, I see that 2n squared equals to m squared. Therefore, 2 divides m squared. You write it like this, guys. It's not a fraction. It means 2. When you have a vertical line m squared, it means 2 divides m squared. You agree? 2 divides m squared. Now, if 2 divides m squared, it means that 2 must divide m. It's a prime number. So prime numbers must be, if it's brought by 2 copies of m, that must be brought by each copy of m. So if 2 divides m squared, then 2 divides m, which means m is equal to 2 times k. 2 times some number. Good. I am worried a little bit, guys. Do you understand me? I'm saying something simple, but maybe you don't understand me still. I'm not sure how much you understand about division or such things. So 2 dividing m squared must imply that 2 divides m. It's true about prime numbers always. So that means m is equal to 2 times k, which means that 2n squared, which is equal to m squared, is equal to 2k squared, which is equal to 4k, which now implies that n squared is equal to, just divide, n squared is equal to 2k squared, which means 2 divides n squared, which means 2 divides n. But that is a contradiction, guys, because I just said that m and n are not divisible by any number other than 1, in simplest terms. Yes? So that means that root of 2 cannot be a fraction. It is impossible for it to be a fraction. And so when you type in your calculator and the calculator spits 1.414, whatever this number, this is a fraction. So this is not root 2. It is not root 2. The calculator is not showing you root 2. Okay, I mean, you think, okay, so what am I getting with it? Do you understand, guys? There was some person named Hypatius of Metapontum. And for talking about this particular thing, at least so the legend goes, the Pythagoreans, they killed him. Now, why would they do that? Is it a very important thing that he that he revealed, a very dirty secret? Okay, you can, if you do the calculation, you would see that root of 3, root of 5, root of 6, root of 7, they cannot be fractions. You understand? I mean, you can make a proof by understanding how certain things work. You prove that those things cannot be fractions. And you call it irrational numbers, but just giving it a title like this doesn't tell you what it is. Now, do you care? Now, you know, there was the next example I think that I'm going to show you guys. I came up with it when I had to teach a low-level class a while ago. And the students were so indifferent, they got me so irritated. I said, okay, some people were even kissing there in the back of the room. I mean, they could not care less about what I said. And I said, okay, then you will not mind if I drop a huge brick on your head. Now, why is that the situation? Let me try to explain to you what happens. Okay, guys, so let's use root of 5, okay? So whether or not we have a fraction or not, whether root of 5 is a number or not, is very significant both in what will happen to you if I drop the brick and in my trial. If somebody is to record it on video and send me on trial for committing a murder. Okay, let's try to understand why, guys. So here, an indifferent, annoying person that I see all the time. And here I will do this experiment. I take a brick, hover it exactly 5 feet over your head, and let go. And I'll select a huge brick, you know, the kind of brick that I have on my soul, on my heart. Huge. And I let it go. What will happen? Well, let's try to analyze it mathematically, guys. Let's try to understand mathematically what would happen. So first of all, guys, I mean, let's ignore air resistance. In the absence of air resistance, Christiana, you are getting there, exactly, right? You're getting to my point. Okay, so you understand, we just verified that root of 2 is not a fraction. And when you say irrational number, you're not saying anything. You say root of 2 is not a fraction. What sort of thing is it? When your calculator is typing then the answer to root of 2, that's incorrect. Right? It gives you a number that's a very good imitation to root of 2. If you square it, you get something close to 2, but you don't get root of 2. You don't get 2. You understand? You get something different. Now, is it something important? So let's try to look at it. 5 is of the same type. 5 is a similar number. So if I drop the brick, yes, it's a similar thing of never reaching the door. Exactly, right? Some of you are seeing my my point. If I drop this brick 5 feet over your head, the question is will something happen to you? And if it does, am I liable? Because look at it, guys. If root 5 does not exist, and the traveling of the brick in free fall is 16t squared, the brick makes contact with your head precisely when 16t squared, at the moment when 16t squared equals to 5. You follow? 16t squared has to equal to 5, which means that t has to equal to root 5 over 4. Now, if root 5 is not an existing quantity, that means that there is no moment of time where the brick makes contact with your head, which means either nothing will happen to you when the brick is dropped, or if it does, it's completely by accident, right? It's not because I dropped the brick, because the brick was not the cause of the impact. It's just the brick falls and suddenly you fall to the ground. And therefore I'm not liable to the damages. You understand? Either the brick is not causing the concussion, or there is no concussion, nothing will happen to you. One or the other must be the situation. There is no time of contact, no time of death. Of course, many people have very thick skulls, so that's another thing here. So now, guys, so then of course it's only in the 19th century where precise description of irrational numbers was well, developed. You understand? What is real numbers is a very, very difficult topic. One second. So Jahin says it's like, okay, what was the establishment of roots for non-prime numbers then? Because what else would be the application? Well, there are many. You see, in essence, root of 5 is a sort of theoretical thing, right? In terms of application, is like if you try to understand such things as cause and effect, it is important, of course. You see, what you have is, in the description that you have now, is that you have approximations, and I'm going to show you now a very, very approximation that you could have actually come up on your own with. You ready, guys, for that? An approximation that what is the calculator doing? I can show you one possibility of how your calculator could figure out root of 2 and root of 5 and all those numbers. But what you have is you have like a theoretical limit, like root of 2, all those things, like a theoretical limit of where the approximations are leading. It's useful, at least in pinpointing a discussion. Mostly with what you operate in approximations, but there is a sort of the approximation is supposed to be more and more focused, and this is the theoretical focus that it has. Also would be real numbers here. So let's say, guys, if I asked you to calculate an approximation to root of 2, let me show you how funny can that description be. Look at it, guys. I will do something that seems useless. Ready? Look at it, guys. Let's take root of 2. Now, root of 2 is the same as 1 plus root of 2 minus 1. Do you agree? I didn't do anything here. I just added and subtracted 1, correct? And look what I can do here. I can multiply by the conjugate. So this is the same thing as 1 plus, I just multiply this part by a conjugate, and that would be 2 minus 1 divided by root 2 plus 1, which is simply 1 plus 1 divided by root 2 plus 1. Are you with me? And now look what I can do, guys. Look at this box. Okay, look at this box and watch it carefully. Look at it. Did I do anything? It seems that I just multiplied by the conjugate, but I just made the expression look complicated and nothing more, correct? Now look what I can do. This is 1 plus 1 over, I can make it look like this expression. I can write it as 2 plus root 2 minus 1. Still, it seems that I have done nothing, but look at this red box. This red box is equal to this entire thing. But it's also equal to this thing. Now I can then take this full thing and plug it in here. And look what I get. So I can say now that this is 1 plus 1 over 2 plus 1 over 2 plus 1 over 2 plus 1 over 2 forever. Do you understand what I do here is that I just replace this piece by the full thing. So I replace this by 1 plus 2 plus plus this box, and this box again by 1 plus 1 over 2 plus 1 over 2 plus. You follow? Can you see it? This box is this thing. So whenever I see it over here, so this box I can replace by the full thing. So when this red box, I can write 1 divided by 2 plus, and then again I have this box, and then I can replace it by 1 over 2 plus, and I have this situation. Now, how does it help me? So look what I can do. I can begin at some number. You see, I see the 1/2 here, right? So I can say my initial, so I have 1 plus something. So I have approximation. So first approximation is, this is what, before I say the approximation, this is what this means. This means that if I have an initial estimate of the number, I can call this initial estimate A1. Then A2 will be 1 over 1 plus over 2 plus, sorry, A1. And in general, AN will be 1 over 2 plus AN minus 1. So this is what I just established. Look at it carefully. So that means that my first approximation is 1 plus 1/2. My second approximation, so this is approximately 1.5. Okay, my second approximation would be 1 plus, what do I do with this 1/2? I write 1 over 2 plus 1/2. Do you see what I do here, guys? I just I create this 1 over 2, 1 over 2, 1 over 2 thing. I take this 1/2, I put it here. And what do I get? I can multiply it by 2. It is 1 plus 2 over 4 plus 1 over 5. So it's 2 over 5. My next approximation is going to be 1 plus 1 over 2 plus 2 over 5. And what is that? This is 1 plus, I need to multiply it by 5. It will be 5. 5 times 2 is 10 plus 2 is 12. So 5 over 12. Here is another one. 1 plus 1 over 2 plus 5 over 12. What do I get? I get 1 plus 12. You understand? I multiply top and bottom by 12. 12, this would be 24 plus 5, which is 29. Right? 24 plus 5 is 29, right? So it's 1 plus 12 over 29. And let me have, here's another one. 1 plus 1 over 2 plus 12 over 29. And that's 1 plus, well, I can write here 29. This would be 38 plus 12, right? The 29 times 2 is yeah, 29, right? So it's I meant it's what? It's 58 plus 12, correct? 58 plus 12. Yes, 58 plus 12 over here. And what do I get? I get 62, correct? Make sure that my algebra is not bad. Now let's see what this is. If you were to type it, it's 1 point. What's 29 divided by 62, guys? If you make it into decimal expansion. Look what I get. I get 1.467 blah blah blah, right? But if I press root of 2, I get 1.414. So you see, I'm already getting the first 2 digits here. It's 70, right? 70. Thank you, right? 70. I said 62, but it should be 70, right? So it should be 29 over 70. Thank you for correcting. Right, so let's see what we have then. It's 29 over, so how many digits do we get? So 29 divided by 70. Oh, it's much better. So here is what we get. We get 1.4142857 and something else, right? And then if I take root of 2, I get 1.414213. Look how many digits I have. I have 4142. 4142. You see, just doing this operation 5 times, I get so many digits. I get huge many digits of root 2. Isn't it impressive? I showed you, and it's your favorite thing, completing the square. You can come up with such a process almost, right? It just seems like it's pointless, right? You make this thing and then you convert it, and what are you gonna get? But it's this thing that at infinity you're getting root of 2. Isn't it interesting? Do you want to try to calculate root of 5 this way, or root of 3? Yes, of course you do. All right, guys, see if you can figure out root of 3. If you understood this idea, maybe that would be extra credit on an exam, right? You will show me how you carry out these calculations. What is root of 3? All right, show me the digits, Giovanni, and I'll show you in a moment what we do here. Did you understand, guys, the idea? How did we come up with this approximation? Is that we're seeing that we are getting, it's called continued fraction. We're getting a box within a box. We're getting, the object is within itself. Here is a hint a little bit, right? So what is this? This is the same as what? What is a root of 3? It is 1 plus root 3 minus 1, right? Now I look at this object, root 3 minus 1. Can I create some sort of self-similar pattern? You see, I want this to be a fraction less than 1 when I do it. Okay, let's see, Jet. So are you ready, guys? So what do? I multiply it by the conjugate. So this is 1 plus, if I multiply it by the conjugate, it's 3 minus 1 over root 3 plus 1. So that would be 2 over root 3 plus 1. Am I right? And what is that? I can write it as 1 plus 2 divided by 2 plus root 3 minus 1. Do you see why? Root 3 minus 1 is that I want the same initial thing. So let's look at it. So now I have those boxes. I have this is the same as that, which is the same as this. I can just plug it in again and again. So what do I get? I get 1 plus 2 divided by 2 plus, this is now, this box is also 2 divided by 2 plus 2 divided by 2 plus 2 divided by 2 plus, and forever. Good. Now you can see that if you want to, you can actually simplify those 2's. You can write it, you can cancel the 2's out. So it's like 1 plus, let's see what we can do here. If I divide this by 2 and I multiply this by 2, so that would become 1 over 1 plus 1 over 2 plus over 2 plus plus 1 over 1 plus 1 over 2 plus and onwards, right? You can simplify it this way if you want to. So it means that, well, let's see if you what you prefer. You can use the top line or you can use the bottom line. It's up to you. So this is what you can now do, guys. You see, it's 1 over 1 plus plus the alteration of 2's and 1's. So that means I can calculate root of 3 by this procedure. 1 plus 1 over, begins with what? It begins with 1 plus 1/2. Take it like this, which is 1 plus multiplied by 2, so it would be 2, and here we have 3, 2/3. Then second procedure, it's 1 plus this number, 2/3, it's 1 plus 2 plus 2/3, which would be 1 plus multiplied by 3, so it's 3 over 6 plus 2, which is 8. Then 3, 1 plus 1 over 1 plus 3/8. This will be 1 plus 8 divided by 8 plus 3, which is 1 plus 8 over 11. And fourth, maybe something like 1 plus 1 over 2 plus 8 over 11. That would be 1 plus multiplied by 11, so it will be 11, 22 plus 8, 30, right? 22 plus, so 11 times, I just multiply top and bottom by 11. So 11 over 22 plus 8, which is 30. Good. So what is that number? That number is approximately 1.11 over 30 is what? So it's 1.36, whereas if I press root 3, okay, root 3. Yes, so we have to be sure that I didn't make something. So that would be 1 plus 1 over 1 plus 11 over 30 would be what? It would be 1 plus 30 divided by 30 plus 11, which is 41, correct? Which is approximately 30 over 41. So that would be approximately 1.73170 as opposed to root of 3. So root of 3, according to the calculator, is 1.73205 and onwards, right? So you can see that I already have 1.73, 1.73. If I get a few more iterations, I will get more digits. Good. In fact, guys, how do you select the algorithm? Because I can tell you, you can, I'm hoping it's good. I'm not sure if you understand. You can take, if you don't like, I simplified it. I'm worried maybe you don't like the algebra. So I can explain more about it, guys. If you want to use, you can use this fraction. Just what's the number that you begin with? Actually, it can be any number smaller than 1. It will bring you where you want to go. Any number here smaller than 1, so you can now select 1/2, but not, it will bring you where you want to go. Okay, so what you do is essentially, you see, this is the formula. It's 2 over 2 plus something. It's the formula. The recursive formula is that an is equal to 1. Well, it's this part here, right? Let's just say this part is equal to 2 divided by 2 plus the previous term. You see this thing? So where you can just select some number. Let's say you can select 1/2, and then you can just take 2 over 2 plus 1/2, and you can just build it up this way. It would work. I just did it so that you would have, you would not have to simplify. You see that the fractions are in simplest forms. Good. Okay, so let's see. So Gabi, good that you came. Good that you came. You just missed roots, how to calculate roots of 5, roots of 3, and whatnot. I hope, guys, you're excited to have this on your, possibly having such a process on your take-home exam. Yes? But that's extra credit. I will not make you do it as a main thing. The extra credit can be anything, hopefully interesting. So let's stop the lesson here. We're at the time, right?